as per my first video in the playlist, any letters you see here are going to be square invertible matrices, which are finite. They're not going to be infinite dimensional, otherwise we get into something complicated called functionals. But first, let's show that SU quantity squared does not equal S squared times U squared. Well, that is not true, because matrix multiplication is not commutative. If we were to break this up into a pair, we would get the string Susu here. We're not allowed to bring the S's and group them together and get the U's to group together, so by this regard, they're not equal to S squared U squared. That's it. This problem is done here. Now let's write down another equivalent expression for UR plus R. So with the real numbers, we have a we have a multiplicative identity, which is simply 1. Any element of the real numbers, let A be a real number. We take A and multiply it by 1. We just get A back itself. Now, if we're doing with a matrix, on the other hand, let A be a square matrix. Square invertible matrix. It's not 1 that we multiply together that gives us back the matrix. Otherwise, that would be scalar multiplication. We have to multiply by a matrix with a matrix, but it would be A is multiplied by the identity matrix for any n by n dimensions will give you back the original matrix itself. And so what we can end up doing with UR plus R is we can factor out an R from the right-hand side, which will leave us with U plus the identity matrix of the size of interest times R. And that's basically that problem done. Now show that 2 times RT equals 2R, all that quantity times T, and that equals R times all quantity 2T. And what does this suggest about scalar multiplication? Well, that's true because, like, unlike matrix multiplication, scalar multiplication, we can move the numbers around as freely as we want when multiplying. So then that explains that. I hate to say this word because it's some pedant or something, but then, like, this is obviously true for, like, that reason. And in general, I can let 2 be any scalar, call it k. And then that same result will also hold as well, that I get that KRT equals KRT equals RKT. And what this suggests about scalar multiplication is that scalar multiplication is associative, which basically means that I can group, using parentheses, the operations so they can be performed left or right in any so order you choose. Note, however, associativity is not the same as commutativity. And the best way I can think of it is this. Associativity, we are allowed to put barriers down, and that restricts what operations you can do. Commutativity, on the other hand, you are allowed to physically move or displace the elements around. Due to the matrices. I shouldn't put elements here. That makes me think that implies, like, the component-wise pieces. Displace the matrices around, then apply the operations. And that's it. 3 quick easy problems done. I hope this was useful. Thank you.